Hello, good evening, students. This is assignment questions. These are assignment questions that I had given earlier in Edmodo. I am just solving the same questions now. Uh, okay, let me begin with this. A strip of paper is attached to a heavy object. Okay, so you see this, we have this in our lab also. Okay, so you have this one here. So the object is dropped and falls to the ground. So it appears like this over here. So you have a spindle like this. Okay, and then there's a paper over here. There's a paper roll. And attached to this is you put across an object over here. And then the moment you drop it, okay, so there's a timer. So, and then there's a tapping machine over here. It just taps the points. Okay, so that's what happens. You get several points over here. The timer marked dots are at an intervals of 0.02 seconds, which means this is at t equal to 0 second. This is at 0.02 seconds. This would be at 0.04 seconds. Okay, you see, at equal intervals of time, the distances are different. Okay, show how the dots on the paper strip show, state how the dots on the paper strip show the object is accelerating. So the question is a logical question here. See, if the particle was what you call, okay, the particle was traveling, okay, or the dots were equispaced like this, okay, 0.0019 meter, and again once again after 0.0019 meter, if you get, okay, that is 0.02 seconds if the dot was at a distance of so much, and once again at 0.02 seconds, okay, if you have one more dot, that means equal distances in equal intervals of time. That's what we can say. In other words, if you calculate what is the speed at which the dot is being seen, okay, so this will be this distance divided by time taken, then again this distance divided by time taken. Okay, so this distance divided by time taken. So as a result of this, you can see the distance divided by time will always remains a constant. So that will be the case when you have something called as a uniform velocity or uniform speed. But here you see, okay, in the first 0.02 seconds, distance was smaller. Then here it was 0.04 seconds, which means in the next 0.02 seconds, the distance traveled is much larger as compared to this, right? So which means it is traveling larger distances in the same interval of time, which means the particle's speed has increased. In other words, there's an acceleration being observed. Okay, so the answer that you need to write here is that larger distances in the same interval of time implies that there is an acceleration. Okay, next. Calculate the average speed of the object in the first 0.02 seconds after the object is dropped. Average speed. What is the definition for average speed? Average speed is equal to total distance divided by total time taken. Now let us see here. So in this case, the total distance is 0.0019 and the time taken is 0.02. 0.0019 divided by 0.02. Calculate what is this value, you will get the average speed, because he has asked you only for 0.02 seconds. Okay, you can always ask me why only 0.02, why can't I do it for the whole one? If he had asked for 0.04 seconds, then definitely you should take 0.07 seconds, there's 0.0776 meters divided by 0.04. Okay, now let us move on to the next one. So whatever is the answer you get here, let us calculate this value. So this value, let me use my calculator. Just give me a moment. Okay, my calculator is on. Right. So this will be 0.0019 divided by 0.02. The answer is 0.095. 0.095, and the unit here is meter per second. Okay. Remember, you should write the unit, otherwise you will miss the mark over here. In the second 0.02 seconds after the object is dropped, in the second 0.02 seconds, the first 0.02 seconds I use this distance. In the second 0.02, that means here what is the average distance? What is the average speed? That's what he's asking. So therefore, let us see the distance covered from this point to this point is 0.0076. So therefore, if you ask me what is the distance covered over here, this would be 0.0076 minus 0.0019. What will this value be? Just calculate that. This would be 0.0076 minus 0.0019, right? 0019. So which should be equal to 0057, which should be 0.0057. So now let us use this value. So the average speed in the second 0.02 seconds is 0.0057 divided by 0.02, which should now be divided by 0.02, which should be 0.285. 0.285 meter per second, right? Okay, now let us see the average speed is not same. It doesn't matter, it should change. Use the results from B to calculate the acceleration of the falling object. You need to find out the acceleration of the falling object. Now, how do we do it? What is acceleration given by? Acceleration is given by V minus U divided by T. Okay, and then if you look at the average speed, since the acceleration is a constant, we can also write A is equal to U plus V. No, wait. How do we write? No, we can write. We see here what happens is the particle is dropped. So look at this. Look at this question here. The question says the object is dropped. When I say it is dropped, U equal to 0, right? So now what we need to do is you can put U equal to 0 and you get V by T over here. And what is T? T is already known to you. You can either take 0.02 here or 0.02 seconds or 0.04 over here, the final velocity. But anyway, let us consider over here. Now we need to find what is the velocity at this point. At this point, we need to find the velocity so that we can substitute here. Now, how do we do that? Is a bigger question here, right? So how do we do it? Any idea? Now I said that it's moving uniformly. So we know that the distance traveled is equal to U plus V divided by 2, average velocity multiplied by time taken. Let me put U equal to 0 here. So you get V by 2 multiplied by time. What is time? 0.02, which we already know. And what is the distance? 0.0019. How did I get this? So look here, 0.0019 is equal to U plus V divided by 2 into time taken. Okay, now let us start with this. So therefore, which means that V should be equal to 2 into 0.0019 divided by 0.02. Now let us calculate that value. 2 multiplied by 0.0019 divided by 0.02, whose answer is 0.19 seconds. 0.19. What is the unit over here? See, this is velocity. Meter per second. 0.19 meter per second. What is that we have got now? Only velocity. We didn't get the value of the acceleration here. We need to substitute it over here. So this should be 0.19 minus 0 divided by what is the time taken? Time taken is nothing but 0.02. Now let us calculate what is that value divided by 0.02 will now be equal to 9.5 meter per second square over here, because it is meter per second here and then divide by second. So therefore meter per second square. So this is the answer for the acceleration. Next, complete the table below to identify the physical quantities as scalars or vectors. Now scalar, speed is a scalar, velocity is a vector, then distance is a scalar, force is a vector. Kinetic energy, what is kinetic energy? Energy is expressed in terms of joules, right? This is a scalar. How is it a scalar? Let us see that also. Okay, so we know that kinetic energy is given by F. Okay, I would just say that, okay, kinetic energy, let us say, for example, I have an object. I say I have given an energy to this object. Let us say 50 joules of energy I have given. Okay, so do I say that I have given the energy in this direction, that direction, so on? I don't say anything about it, right? So therefore, 50 joules is nothing but a scalar quantity. So thus, this appears to be a scalar. Kinetic energy is a scalar. Then, figure shows the path of a football as it is kicked from the ground between 3 players. The distance between the players are shown in figure 1.1. Okay. The ball takes 1.2 seconds to travel from player A to B. From player A to B, it takes how much time? It takes a time of 1.2 seconds. Okay. Calculate the average speed of the ball between A and B. Very simple question. So average speed here, average speed. Okay, let me write down. V average for AB is equal to total distance, that is the distance AB divided by time taken. What is distance AB? 18 meters. What is time taken? 1.2 seconds. Let us find out what is the value here. 18 divided by 1.2, which will be 15. So which is 15, unit is meter divided by second. So the average speed of the ball is seen to be between A and B is 15 meter per second. Next, player B kicks the ball to player C. Okay, he clicks from here. It travels with the same average speed, which means the average speed here is seen to be 15 meter per second. Okay, then calculate the time taken for the ball to travel from B to C. So here, what is the time taken? Okay, now we do not know what is the time. Now, what is the definition for average speed? Average speed definition, V average is equal to the total distance traveled, which is BC divided by time taken, right? Now we have the BC value. What's the BC value? 21 divided by time taken. I do not know. That's what I need to find. 21 by T. So now T should be equal to 21 divided by, now you see this value is 15. I copied from here. Why did I copy? Because it says it travels with the same average speed, right? 21 divided by 15, which should be equal to how much? Let us find that also. 21 by 15 would be 1.4. Unit, what is the unit over here? See, this is in 21 was in meters. This is meter per second. This is meter per second. This is meters. So meter and meter cancel. Second goes afterwards. This is 1.4 seconds. Okay. Then now let us move on to the next one. Suggest why the speed of the ball might change during its motion from A to B. Now, when it moves from A to B, is it A to B or A to C? Suggest why the speed of the ball might change during its motion from A to B. Okay. Now, football as it is kicked along the ground between three players. Now, as it is moving, so why should the speed of the ball change? Any idea? If it is moving along the ground, friction can also play, okay, an important role, right? So as a result of it, the speed will not be the same. Okay, that is the reason why we take the average speed, right? Otherwise, I would have just taken, okay, whatever speed he has kicked it. He would have kicked it at a much higher speed. But as the ball starts rolling here like this, you will be able to observe that the average speed will not remain, sorry, the same speed will not be there. The speed may reduce over here, right? So therefore, the speed reduces. Why should the speed reduce? Because of friction. Friction can be one of them. Air resistance can be one of them. Then any stones, okay, then it can have a bump, okay, on the ball, on the ground, on the pitch. It can bump like this and go over here. It may lose some energy here, right? As a result of this, the speed of the ball might change. Discuss whether the average velocity from A to B and B to C are the same. No, that is a 1 mark question. So we have determined that VAB and VBC averages are not equal, right? Magnitude, via magnitude also, and direction also changes. Why should I highlight on direction? Because you read here, average velocity here. It is not talking about average speed. Okay, by some chance, if suppose if you have spoken about average speeds and these are equal, okay, then you can just write like that. But let us say average speeds were equal, but still he has asked about average velocities. Still you can say, okay, that the magnitude might be same, but the direction is changing. Direction is also changing. Okay, see, both the points are very important for this 1 mark. Right, then a bus travels at a constant speed. Now this is a distance versus time. So whenever you have a distance versus time graph, constant speed means it will be like this, right? It stops for a short time. That means the distance is not changing with respect to time. Stops for a short time, and then travels at a higher constant speed. Now, first thing that you need to understand here is that the slope of this graph gives you the speed of the object. So here, this slope will be this much. But if you want a lower slope, this would be a lower slope. If you want a higher slope, this will be a higher slope. So therefore, if this is O, this is point A, OA represents this one. this region. This sentence is represented by OA. It stops for a short time, which means, let us say this is AB. This represents AB over here. And then travels at a higher constant speed, which means what? I should have a much higher slope. The line should not be parallel to this. It should be something like this. So from here, I will draw like this over here. Let me put AC here. Let me see here. Okay, so this will be your BC. Draw a distance time graph for the bus journey. We have drawn it. Right. Next. Figure 1.1 and 1.2 show speed time graphs for two objects, each moving in a straight line. Okay. Describe the motion of the object as shown by the graph. This is, remember, speed time. See, if you take the slope, what do you get here? This is change in speed versus time. What is change in speed versus time? Acceleration. And you see, the slope is a constant because it's a straight line. So therefore, this is a uniformly accelerated motion. And don't just write here like this because the keyword here is describe. Okay, it is uniformly accelerated motion since the slope is constant. You need to elaborate your answer like this. Right. Now let us look at the next one. Describe the motion of the object shown by graph 1.2 here. Now, as I said, in a speed time graph, you need to draw a tangent. Okay, let me draw a tangent here. This is a slope. Okay, find the slope of the tangent here. This would be your slope. Let me take another point. This would be my tangent. Let me take another point here. This would be my tangent. Now you see, at every point I have drawn a slope. Now let us say, for example, this slope is named as M1, this is M2, this is M3. And we know slope is given by changes along the y-axis divided by changes along the x-axis. The change is represented by the letter delta here. See, the triangle that I have represented here is nothing but delta. So which means the rise divided by base. That's what you call, right? Now you see here the rise is much higher and the base is much smaller. If this is smaller, slope will increase. And if this is larger, slope will increase. So therefore, what you conclude from here is that M1 is the largest slope, M2 is the next largest slope, M3 is the next largest slope. Which means, now what does this slope tells you? Here, the slope tells you there is an acceleration A1, this is acceleration A2, this is acceleration A3. Which means you see, the acceleration A1 is very, very high. Then as it keeps on going, the acceleration reduces, then acceleration still reduces. If it keeps on going like this, sometimes the acceleration can be much more minimal. That means the change in velocity over time is reducing slowly. Okay, when the acceleration is reducing, what do you call that phenomena as? We'll call that as deceleration. Okay, so you will say this is this uniform? Is this uniform? You see here, when I talk about uniform, the acceleration will be remaining a constant. Okay, here the acceleration is not a constant over here. So you have to write two things over here. First is this is a non-uniform motion and the particle is decelerating. Okay, then on a day with no wind, a large object is dropped from a tall building. Okay, you have a tall building, maybe your apartment building, right? The object experiences air resistance during its fall to the ground. So you are dropping it here. It expects the air resistance. State and explain in terms of the forces acting how the acceleration of the object varies during its fall. The moment you drop here, what will be the acceleration? A will be equal to G. But as it is coming down, it faces an air resistance. Okay, this will have a force mg. I'm drawing the free body diagram. This will have one more force, which is nothing but your air resistance. Okay, since the body is still coming out downwards like this, you can say mg minus f is equal to m into a, right? In other words, a should be equal to g minus f divided by m. Okay, which is a constant. Now you see, okay, as it keeps on coming down, okay, the acceleration is seen to be reducing, or sometimes there's a possibility that g will become f by m. Okay, now what we'll do is we'll say, now let us understand what's been given. How many marks is this? This is given for 3 marks, right? No, this was for No, this mark is not for 3. This was for state and explain. Yeah, this could also be for 3 marks. 3 marks here. State and explain in terms of the forces acting. What are the forces acting? The mg force is acting downwards. F force is acting upwards. That is the air resistance acting upwards. How the acceleration of the object, varies during its fall. So acceleration of the object varies during its fall based on this way. Okay, so you need to mention all this. Then at a sports event, a champion runner and a car take part in a race. Champion runner, there are 2 objects. Okay, the runner runs at a constant speed of 10 meters per second from the start of the race. A runner runs at a constant speed of 10 meters per second. During the first, this is a constant speed. During the first 5 seconds of the race, the car speed increases from 0 meter per second to 25 meter per second at a uniform rate. First 5 seconds, see, t is given to you, initial velocity is given, final velocity is given, which means definitely you can find out the acceleration, right? Okay, now what is he asking here? He's not asking you the acceleration. Okay, this is one of the grave mistakes, everyone does it, including me. Okay, so what you need to do is, you need to read the question, you need to understand what parameters are given, what is being asked. So what is being asked here? A graph to show the motion of the runner. Okay, so we will draw a VT graph. He has not asked you what graph you want to represent, right? See, nowhere he has represent. You need to represent it using a VT graph because you're talking about the motion of the runner. Now, so what happens here? The runner runs at a constant speed of 10 meters per second because you don't have any other data with you. You cannot draw an ST graph or an AT graph. Okay, you can always represent the motion using that, but unfortunately you don't have anything with you, right? So therefore, constant speed of 10 meters from the start of the race. So from the start of the race, let us say this is V equal to 10. He keeps on running with the same constant speed like this as time progresses. So this is for what? This is for the man. This is for the runner. Okay, this is for the runner. Then a graph to show the motion of the car. For the car, this is T, this is V. Now the motion of the car. Now what's happening here? The car speed increases from 0 to 25 at an uniform rate, which means just make a line passing through the origin like this. And then what you do is, this is at t equal to 0, it was 0. At t equal to, what time was it? The time was at 5 seconds. At 5 seconds, the speed was seen to be 25. This is what is the slope here? Slope should be equal to 25 minus 0, right? Divided by 5 seconds, which should be equal to 5 meters per second square. This is your acceleration. Anyway, he has not asked you, but let us see. So here you just need to draw a graph like this. Now let us move on to the next question. Oh, he has already given you, but we have drawn it there. Okay. Use your graphs to determine the distance traveled by the runner in 5 seconds. Distance traveled by the runner in 5 seconds. Let us say this is 5 seconds over here. Distance traveled by the runner would be the area of the graph here. You had to draw it in that graph, but anyway, I've drawn it here. Okay. So area of the graph. What is the area of the graph? This is a rectangle over here. So this is 5. Area here should be 10 into 5, which should be 50 meters. 50 meters. Okay. So I will write this as 50 meters. Distance traveled by the car in 5 seconds. In the same time, what is the distance traveled? What is the distance traveled over here? Area of the graph. This area. We need to find this area, which should be half into 5 into 25, which should be equal to how much? 5 into 25 is 125. 125 divided by 2 would be 62.5 meters. Okay. So let me write this as 62.5 meters. The time at which the car overtakes the runner. Okay. So time at which the car overtakes the runner. How do you solve this? How do you solve this? Now, when I say time at which, okay, let me draw a graph here. Okay, let me draw a picture here. So the runner is moving at a constant speed like this. The car, okay, the car has started from rest and it has started to move like this. Okay, at a particular distance, you observe the runner and the car are at the same point, right? Okay, excuse me, this is my car, looks funny, but anyway, okay, let us go with it. Right, okay, so the runner and the car is at the same point, but you know, the car has an engine, and as a result of it, okay, after 5 seconds, you see that this, okay, at the end of 5 seconds, okay, maybe the car is over here, and at one particular time, both of them were matching. Okay, so we need to find at what time, okay, the distance covered. You see, at that particular time, the distance covered by this person and by the car were one and the same. So why was it one and the same? The reason is because you observe that the person was moving with uniform velocity while the car was accelerating itself. The person did not start. The person here, the runner did not start at what do you call 0 meter per second, but he started with a higher velocity. Okay, but the car is not like that. It started with 0 meter per second and gradually increased its speed. As a result of it, initially for a first few microseconds, you observe that the person was speeding up while the car was behind him. And after that, the car took up its speed. And at one point of time, you observe that both of them were traveling at the same speed. Okay, sorry, where they both of them met together, not traveling the same rate. Both of them met together. So when I say both of them meet together, remember that the distance traveled by the person and the distance traveled by the car, both were one and the same. Now towards it, what we need to do, let us use this. So distance traveled by the person is equal to V into T, right? In a time of T seconds, you need to find what is the T, which I do not know. Distance traveled by the car is given by ut plus half a t square. Now towards it. Now what is V here? Let us go back. What is V? The constant speed. What is the constant speed of the runner? 10 meter per second. 10 meter per second. So I'll write this as 10 into T. I do not know what's the value of T. T is not 5 seconds. Okay. T 5 seconds is nothing but the end of the run. Okay. But somewhere in between, both of them met once again. That's what I just put it across as T. And now this is for the car. And for the car, you observe that the initial velocity was 0. So you just had half a t square. This is what you had. Okay. Let me equate one with the other. Why should I equate here? Because the distance traveled by the person and the distance traveled by the car, both are one and the same. Thus, you will write 10t is equal to half a t square. Now I need to get the value of a. What is the value of a? Look at the graph once again. So we determine the value of a somewhere here, right? Which was seen to be 5 meter per second square. How did I get this? I drew the graph. I found out what was the slope, and thus I got the slope as 5 meter per second square. So let us take that also. And now I will say 10t equal to half a t square, which should be a half into 5 into t square. 10t is equal to half into 5 into t square. This square, this t goes away. 5 ones are, 5 twos are goes away. So you get, push this 2 on the other side, you get 4 is equal to t r. T is equal to 4 seconds. So which means that at the end of 4th second, okay, the car and the runner, both of them meet together. But after that, what happens? Within the next 1 second, the car overtakes the person, the runner, and thereby it becomes first. It comes first while the runner comes last. Is this clear? Okay. Now let us move on to the next one. On figure 3.1, okay, draw a graph of extension against load of a spring which obeys Hooke's law. Hooke's law, what is Hooke's law? F is equal to minus kx. So he is asking you the load of a spring which obeys Hooke's law. Load, okay. So this is the load along the x-axis as you increase. So what happens in Hooke's law? We had shown this in the experiment also. You add the masses over here. I keep on adding weights over here. Okay, and I had shown you the spring here keeps on increasing like this, right? Keeps on increasing like this. Keeps on increasing like this, which means the extension here is larger and larger over here. When does it increase? It increases when the weights added here is increasing, right? That's what we had observed in the lab also. So therefore, as the weights added, or what you call as load added increases, extension increases, which means that I should be getting a straight line like this. Okay, then state the word used to describe the energy stored in a spring that has been stretched or compressed. What is the energy stored in a spring? So how many energy storage are possible? One is the potential energy, other one is the kinetic energy. What is kinetic energy? When an object moves from one end, okay, then, okay, if it is in motion, then it is kinetic energy. But while in case of a spring, you observe that the spring does not move anyway, right? You put a spring like this, you put an object over here, though the spring expands like this or it contracts like this, okay, but still the spring itself does not start moving, right? So therefore, this is not kinetic energy. Why? This is the potential energy. This is the potential energy, right? Then figure shows a model train traveling at speed v approaching a buffer. Okay, you would have seen this in railway stations. So you see at the end of it, there's a buffer here, which means it has a metal plate, and attached to the metal plate, okay, is a big spring over here, very, very stiff spring. So that if accidentally the train comes and hits it across, okay, it will be able to resist it. That's why this buffer is being put over here. You see, spring is kept over here. A train of mass 2.5 kg. 2.5 kg is very less. Oh, it's a model train. Okay, it's a toy train. 2.5 kgs is stopped by compressing a spring in the buffer. After the train has stopped, the energy stored in the spring is 0.48 joules. Calculate the initial velocity of the train. So what happens here is, there's a moving object. When you say it's a moving object, the energy associated with the moving object is half mv squared, right? So it goes, it hits it. The moment it hits it, what happens? All the kinetic energy of the train is given to the buffer here. That's what it says. So when you say it is given to the buffer, that means the spring which was extended like this, once the train hits it, okay, then this starts compressing, and then it becomes like this over here, which means all the energy is given. It compresses until that level wherein the train is completely made to stop, right? So that's what is happening. So therefore, calculate the initial speed of the train, which means what? When the train is traveling with the speed v, what was the initial speed? So how do I do? We know that. Now, when I say the energy stored in the spring is 0.48, which means, okay, so before the train came and hit the spring, there was no energy in the buffer. It was zero energy. So why did the spring's energy rise? Only because the entire energy was transferred like this. So as a result of this, I can now equate half mv square equal to 0.48 joules, right? The energy in the train is given to the buffer spring, and as a result of it, the energy increased. That's what we have done. Okay, so which should now be half into 2.5 into v square is equal to 0.48. Let us solve for this. V square should be equal to 2 into 0.48 divided by 2.5. So how much will this be? Let us calculate that also, which should be 2 multiplied by 0.48 divided by 2.5. Okay, so which should be equal to, you should be getting an answer equal to 0.384. And if I take the square root of it, 0.384, you should get the answer as 0.619, 0.62. 62, what is the unit? Velocity, meter per second, right? Okay. Okay, then. Figure 2.1 shows a rock that is falling from the top of a cliff. Okay, from a top of a cliff. So this is the cliff over here, fell into the river. This is the falling rock. This is a river over here. The mass of the rock is 75 kg. The acceleration of free fall is 10. Calculate the weight of the rock. Okay, weight of the rock. What is the weight of the rock? Okay, whether it is falling or standing or whatever it is, the weight of the rock is always given by mg. Okay, straightforward question. 75 multiplied by 10, which would be 750, the unit. Now you see, m into g is weight, right? Weight, which is nothing but the force. The unit of force is Newton, so this should be Newton. Then the rock falls from rest through a distance of 15 meters before it hits the water. Rock falls from a distance of 15 meters, which means the distance from here to here is seen to be 15 meters. Okay, then calculate its kinetic energy before hitting the water. Calculate its kinetic energy. What is the energy here? Okay, now the first thing is that when the rock was on the surface over here, its potential energy was zero. It did not have any energy. But now when you lifted this object to this height, okay, then the energy on this object is seen to be mgh, which is potential energy. When the rock starts falling down, what is happening? The potential energy present in it is getting converted to the kinetic energy. Kinetic energy increases, potential energy decreases, and when it reaches here, the net energy is only due to kinetic and not due to potential, which means that the energy of the rock is seen to be mgh. Okay, so now what we will do is, I hope you understand this. Okay, so I can now write from conservation of energy theorem, I can now write mgh is equal to half mv square. If you look at the question once again, calculate its kinetic energy just before hitting the water. He is asking you, what is the value of half mv square? Logically, we are able to prove that this half mv square is equal to mgh. Show your working, 3 marks. Okay, So you need to write it down. Okay, just writing like this will not fetch you any mark. You need to write from the conservation of energy, from the conservation of energy, conservation of energy. Okay, the rock has an energy equal to mgh, mgh. Okay, at the peak, at the peak. Okay, and when the rock was dropped, its potential energy was mgh, and the potential energy got converted to kinetic energy, and the kinetic energy became maximum when it was hitting the water. And hence we will be able to write half mv square equal to mgh by conservation of energy. For this explanation, you will get 2 marks and 1 mark for the calculation. Okay, so therefore now you need to calculate. See, you do not know the velocity, it doesn't matter. You just need to calculate this mgh. What is the mass of it? 75 kg. What is the value of g? 10. What is the height of the rock? 15. Okay, just calculate what is this value. Let us calculate this. This should be 75 star 10 into 15, which should be 11,250. 11,250 unit joules, right? This is the answer for it. You can also write this as 11.25 kilojoules, right? The rock hits the water. Suggest what happens to the kinetic energy of the rock during the impact. The moment it hits the water, what happens? What do you observe? Does it say, okay, I'm hitting the water and I'm just giving all the energy to it? No. Okay. The moment you hit it, you hear a splash. You hear a splash, which means what? What do you mean by splash? The kinetic energy is getting converted to sound energy, right? Getting converted to sound energy. Okay. And then waves are created. Right? Waves are created, which means when I say splash, the water has been thrown upwards, right? Waves are created. So you can say there's a wave energy also being created, or some amount of mass of the water climbs upwards or is being thrown upwards like this over here, right? The moment it hits it. So this is what happens over here. Okay. Then so here we expect only, okay, so to express yourself about how does the energy transformation takes place. Then state what happens to the molecules of a gas in a sealed container when the temperature of the gas is increased. You have a gas in a sealed container, you are increasing the temperature. What happens? I had asked you the same question in your essay also. Okay, so the molecules which are present here, 2 things can happen here. The first one is the interatomic distance will reduce, right? Which means, let us say this molecule and this molecule was initially much farther away. Now they become very closer. And as a result of it, what can happen? Collisions will be frequent. Right? And when collisions are frequent, then what can happen? Average speed can increase. When average speed can increase, what can happen? Half mv square can increase. What is half mv square? Kinetic energy. The average kinetic energy will increase. See, this much you have to write. Okay, don't just write when this is increased, pressure increases. Finally, pressure increases. It again depends upon what kind of, okay, how much marks has been allotted to a given question. So here, if it is just state, you can just write pressure increases. Okay, or kinetic energy, average kinetic energy of the molecules increases, pressure increases. But somewhere this term is very important. Okay, either you can write kinetic energy increases, average kinetic energy increases, and hence pressure increases, or you can just say pressure increases. But if I say describe what happens to the molecules of a gas, in that case you should be able to write the whole thing. Now, a quantity of gas is contained in a sealed container of fixed volume. The temperature of the gas is increased. State in terms of molecules 2 reasons why the pressure of the gas increases. Again, so in this case, this is for 2 marks. Now all these are fine. Okay, somewhere average speed can increase, half mv square increases, pressure increases. Why does it increase? Because you see, this is my container. Now this goes and hits it over here. Now when the velocity is increasing, so every time the number of molecules which are having collisions over here is much larger, and as a result of it, okay, so when it hits it across, the force acting on the vessels of it, on the sides of the vessel increases, and thus you see force divided by area increases, right? Which is nothing but pressure increases. Okay. For this, you should give two reasons. What are the reasons here? You have to give this reason. You can give this reason, and as a result of these two, this will increase, and then you have to explain this, right? Then a helium-filled balloon, weather balloon is held at ground level. The volume of the a helium-filled weather balloon is held at the ground level. Okay. So it's been tied. Right. It's held at the ground level. This is my helium balloon. The volume of the balloon is 4,800 meter cube. 4,800 meter cube. The pressure in the balloon is 98 kilopascals. Okay. The balloon is released. You cut it, it goes upwards. Okay. So it goes upwards over here. Right. Then and rises to a height where the volume of the balloon is 7,200. Oh my God. How did it increase? 7,200 meter cube. Calculate the new pressure of the helium. Okay. So why should it increase? Any idea? Can you think about it? Because this is an elastic one, right? So it is nowhere confined to one place. So it is an elastic one. So definitely it can increase. Okay, so the volume can increase. So there's a liberty for the balloon to increase its volume. So as the volume can increase, the gas present in it can also increase. Now the question I asked is why should it increase? It's not been asked over here. I'm asking you here. The reason why it should increase is because at this level the pressure will be higher. When it goes to higher altitude, pressure becomes lower, right? Okay, when you go for higher altitudes, we are going on for trekking, then what happens is sometimes, okay, you might see that the blood oozes out of your nose. Why does it happen? Because in the nose, there's a thin diaphragm, okay, which prevents the blood vessels to break from. But when the pressure, outer pressure is much lesser, then the inner blood pressure is much higher, and as a result of it, blood can ooze out, right? Okay. Then the balloon is released and rises to a height where the volume of the balloon is 7,200 meter cube. So here I have got V2 here. We do not know what's the P2. New pressure of the helium, assuming temperature remains constant. So therefore, I have been given P1 is equal to 98. V1 is equal to 4,800. I am not writing the units. P2 is equal to what? V2 is equal to 7,200. Which equation shall we use? Temperature remains constant, which is this Boyle's law, right? So P1 V1 is equal to P2 V2. Okay. So therefore, now you need to find out the value of P2. Quite simple, which should be 98 into 4800 divided by V2. What is V2? 7200. Hope you understand the math behind it. So let us calculate this. There is my calculator. 98 multiplied by 48 divided by 72, which should be 65.33. What is the unit now? See, what was the unit here? 98 is kilopascals. That is where this is very important. This is meter cube. This is meter cube. So this is meter cube. This is meter cube. Cancels, and you have kilopascals here. So this should be kilopascals. So 65.33 kilopascals is the answer here. Now, as expected, here the pressure was higher. Here the pressure should be lower. See, 65 is lesser than 98. So our answer is correct. Okay. Now let us move on to the next one. Suggest why it may be necessary to release helium from the balloon as it rises even higher. Now the balloon doesn't stop here. It keeps on going upwards. Okay. As it keeps on going, let us say the balloon went over here. Balloon went over here. Okay. So what do you expect here? The balloon's volume would have been much more higher over here. Now, while this happens, it is said that some amount of the gas has to come out. You see, necessary to release helium. Okay, you have to open the nozzle and see to it that the helium has been released. Why should it do it? What is the reason behind it? Because the balloon has a capacity to expand, certain capacity to expand. Now, when you keep on increasing the capacity, okay, initially it was only so much. Now, what did you do? Because it went upwards, it became like this. But as it keeps on going upwards, it can become much larger. Can become much larger over here like this. Now, as it keeps on increasing larger and larger, there's a possibility that the balloon might break, right? Okay, so because it cannot expand beyond a particular level, so therefore it is necessary to release some amount of helium so that the amount of gas present in it, is not sufficient enough to expand over here. Okay, so that's why you need to release some amount of helium. Then A student carries out an experiment to find the relationship between the pressure P and the volume V of a fixed mass of gas. Okay, so P versus V is given over here, P in kilopascals, V in centimeter cube. Use the data in the table to suggest the relationship between pressure and volume. You see, pressure, now you see, which is your independent variable here? 250, 500, 750, 1000, 30, 15.2. As you note here, this is systematically been increased. So this should have been your independent variable. Okay, this is your criterion B question. And you see, this should be your dependent variable. Okay, so what do you suggest here? When it was 250, the answer was 30. When this is 500, when this is getting doubled, you see, this is getting halved, right? Now, when 250 becomes 750, that means it's getting tripled over here. You see, 30 becomes 9.8, closer to 10, which means volume, pressure, when it is being made thrice, I'll write it down here. When pressure was made as 2P, volume became V by 2. When pressure was made 3P, volume became V by 3, right? And if you look at this one here, pressure becomes 250 multiplied by 4, 4P here. Then what happens here? Volume became 30 divided by 4, which is around 7.5. You get the answer as 7.6, V by 4 over here. That's what you observe here. You can say that pressure and volume are inversely proportional. Remember, okay, whenever we use the term inversely proportional, we should see to it that the pressure multiplied by volume, okay, in every trial should always give rise to the same constant value. Okay, so like for example, I'll tell you one more example apart from this. Let us say, for example, you have a number like 20. Okay, you can write the value of 20 as 2 into 10, 4 into 5, 5 into 4, okay, 10 into 2. Now you see, either this increases, correspondingly this decreases, so that the product always remains a constant. Whenever you find a relationship like this, then only, okay, say this is one variable, this is the other variable, okay, but then only you can say that these two variables are being inversely proportional. Otherwise, you should not use this term. Okay, now state the property of the gas apart from the mass that remains constant during the experiment. Very easy question. See, when is this rule applicable? The rule is applicable when temperature is a constant, because there's nothing but your Boyle's law, right? Okay, and this has already been as a clue given here. See, somewhere it's not been given. No, it's not been given. Okay, so that's what you understand from here. Okay, next, smoke particles are introduced in a glass box containing air. Okay, this is your glass box, and then smoke particles are here. Smoke particles are here. Light shines into the box so that when observed through a microscope, smoke particles can be seen as bright points of light. So you are now shining light from here. Okay, let us say you're shining light from here and you are observing it through a microscope here. Okay, you're observing it through a microscope. And you see that the smoke particles can be seen as bright points, okay, when the light falls onto it. So definitely, okay, so you're seeing it as bright spots. Describe the motion of the smoke particles and account for this motion in terms of the air molecules. Now, when you see these bright points, okay, how will these bright points be present? Will it be just be at the stagnantly present over here, or will they be just started moving like this? So what will happen? That's what is the question. Describe the motion of the smoke particles. Now we can say that the smoke particles will move in random directions. Random directions. Why do they move? And account for their motion. Why do they move? In terms of the air molecules. Why do they move? Because air has an ambient temperature, the room temperature what has been present. And as a result of this, molecules tend to move randomly and collide with each other, which is nothing but your kinetic theory, right? This is what you need to mention here. Okay, next. Figure shows a quantity of a gas in a cylinder sealed by a piston that is free to move. Okay, so the piston can easily move. You have some gas here. The temperature of the gas is increased. So you are increasing the temperature of the gas. You are heating here. Okay, so you are increasing the temperature. State what happens if anything. Now again read the question. Quantity of gas that is free to move. Nobody is stopping here. When you increase the temperature, then what happens is the volume will start increasing because there's nothing to stop here. Okay. So therefore, what should we write here? Piston moves outwards. What happens to the piston? Piston moves outwards. Okay. You can also write piston moves to the right. Both are correct answers. To the pressure of the gas. What happens to the pressure of the gas? So there's nobody to stop here, which means the pressure is constant. Pressure is constant. And as a result of it, what's happening? The volume of the gas is increasing. Since volume is increasing. Okay. Then okay, just a minute. I'm back. The piston is now fixed in space and temperature of the gas is increased further. Now what we are going to do is, now this is my piston. Now I'm going to stop this. Okay, so I'm not going to make it move further. It's fixed in space. Okay, temperature of the gas is increased. I'm increasing the temperature. Explain in terms of the behavior of the molecules what happens to the pressure of the gas. Now, when I fix this one, this is not going to change, nor this is going to change. Okay, and if suppose if this has a region like this, right? So definitely this is also not going to change. That means the volume is remaining a constant. So volume is constant. Volume is constant because piston is not moving. When the piston is not moving and volume is constant, if you increase the temperature, then the pressure will increase, right? What happens to the pressure of the molecules? The pressure of the molecules will increase. So you need to write the whole thing. Don't just write temperature increases, pressure increases. You won't get a mark here. Okay. Then next question. Complete the following statements. The pressure of a gas in a sealed container is caused by the collisions of dash with the container wall. Which one? Molecules. Okay. As an increase in the temperature of the gas increases the pressure because the dash of the dash increases. What is the dash of the dash increases? An increase in the temperature of the gas molecules increases the pressure because which one increases? Because the pressure, because the speed. So which one increases? Okay, wait, let me read the question once again. The pressure of a gas in a sealed container is caused by the collisions of molecules within the container wall. An increase in the temperature of the gas increases that pressure. T increases, P increases. P increases because the speed of the molecules. The speed of the molecules increases. Okay. So then the force on the wall due to the gas is the pressure multiplied by area of the wall. Right? Because we know pressure equal to force by area. Then a mountaineer takes a plastic ball containing some water to the top of a mountain. He removes the cap from the bottle, drinks all the water, and then replaces the cap. Okay. And as shown in figure 6.1. Okay, there's no water in this. So there's no water. And where was this done? This was on the top of the mountain. Top of the mountain. Okay. And returning to the base of the mountain. Now he is come to the base of the mountain. Base. And if you find that the bottle has collapsed to a much smaller volume, which means somebody is pressed here like this, right? Okay, he did not press it. Okay, when he was at the top of the mountain, this is the condition of the bottle. When he came down, he observed that this has been pressed like this. So when I say this is pressed over here, what do you mean by that? You have applied a pressure. You did not apply. The atmosphere has applied a pressure. Atmosphere has applied a pressure. There also, on the top of the mountain also there was a pressure. Here also there is a pressure here, right? Only thing is the pressure here might be higher as compared to the pressure here. Now we have not looked at the answers to our question so far. Okay, we have just been thinking of what may be the question. Okay, now let us see. Explain why the bottle is collapsed. Okay, why the bottle collapsed? Because pressure at the base is higher than the pressure at the top, right? Okay, so that's the reason why if you use a hero pen, for example, okay, if you are using a hero pen at the top of the mountain while coming down, okay, there's a possibility that the pressure is higher and hence the ink in the pen might leak. You have to be very careful. Okay, so we don't generally recommend people to take up a hero pen. Just take a ballpoint pen, close it carefully so that the pressure is the ink does not leak out. All right, now at the top of the mountain, the atmospheric pressure was 4.8 into 10 power 4 pascals. This was your pressure at the top. And the volume of the bottle was V1. Calculate the volume of the bottle at the base of the mountain where the pressure of the air inside the bottle is P2. Now you see, P1, V1 is given, P2 is given. He is asking you, calculate the volume. V2 is equal to what? Assume no change in temperature. Straightforward question. Only thing is words are being changed here and there. Which rule do you use? You will use P1, V1 is equal to P2, V2, right? Boyle's law. Okay, so that the change of temperature is, there's no change in temperature. So let me apply this rule here. 4.8 into 10 power 4 multiplied by V1. So I'll keep this as 250 centimeter cube only. I'm not going to change the unit. This should be equal to pressure, which is 9.2 into 10 power 4 multiplied by V2. Now your V2 will be in what unit? It will be in centimeter cube only, right? So 10 power 4 here, 10 power 4 here, gone. So your V2 will now be equal to 4.8 into 250 divided by 9.2. Now let us find out what is that value. 4.8 into 250 divided by 9.2, which will be 130.4. 130.4 meter cube. See, the volume of it is going to be so much. A vertical cylinder has a position fitting, well-fitting piston in it. Okay, you have a cylinder. Okay, weights can be added to or removed from a tray on the top of it. Okay, weights are added to a tray. Okay, so you're adding some weights over here. Now, when you add a weight, what can happen? There is an air initially. Without addition of the weight, the piston is standing like this. With the addition of the weight, you are applying a force over here, and this area. Okay, this is the force acting here. Force divided by area. The pressure now increases. So the piston can now get compressed like this. Okay. So it can compress, the air can get compressed. Okay, let us read the question. Then, what is asking? State what happens to the pressure of the air in the cylinder. Wow, we have already answered it, right? Pressure of the air inside the cylinder as a result of adding these weights. When you add the weights, what happens is pressure increases. Simple. Then, state what happens to the pressure of the air in the cylinder as a result of adding this. Oh, I have added two times the same one. Pressure increases. Okay. Then, next. The initial pressure of the trapped air is 1.05 into 10 power 5 pascals. So P1 is given. When the weights are added, the volume of the air decreases from 860 centimeter cube to 645 centimeter cube. This was your V1 initially, okay, without weight addition. With the weight addition, this becomes your V2. Temperature of the air does not change. See, we already got a clue. Calculate the final pressure of the trapped air. What is the final pressure? So what do we do? P1 V1 is equal to P2 V2. What is P1? 1.05 into 10 power 5 multiplied by V1, 860 should be equal to P2. We do not know, multiplied by 645. Okay, we need to find out what is P2. P2 should just be equal to 1.05 into 10 power 5 multiplied by 860 divided by 645. Now let us calculate what is that value. 1.05 multiplied by 860 divided by 645, which is equal to 1.4. So 1.4 into 10 to the power of 5 pascals. As expected, you see, the pressure has increased, right? Because you compress the piston, right? See, here you compress the piston. So the pressure should increase. That's what you assumed, right? You're getting it correctly. Okay, let us move on to the next one. The area of the piston is given. Calculate the weight that is being added. Wow, wonderful. You need to find out what is the weight. So we know that pressure is equal to force by area, which is also equal to weight by area, because force is weight, right? So therefore, the weight is equal to pressure multiplied by area. Which pressure is this? The pressure due to adding this weight, which is nothing but your final pressure, the one which we had calculated here, right? Which is nothing but your P2 into A. So thus W should be equal to, what is P2? 1.4 into 10 to the power of 5 multiplied by area, which is 5 into 10 power minus 3, which is equal to how much? 5 into 1.4 1.4 into 5 will be equal to 7. 7 into 10 to the power of 5 minus 3 is 2. 2. Note that there's two significant figures here, one decimal point. So I'll write this as 7.0 into 10 square. And what is the weight? Weight should be equal to in terms of kgs, right? It should not be in, should be in grams or kgs. Just take it out. So what is this unit? Pascals. And what is this? 5 into 10 power minus 3 meters. Okay. So Pascal is nothing but Newton per meter square. Okay. This is not kg over here. 7.0 into 10 power. So let me write it down. So this is where mistakes we make. Newton into meter square multiplied by meter square. So you get the answer in terms of newtons over here. So this is the force acting here. Okay, weight. Now if you want to find a mass, mass will now be equal to 7.0 into 10 square divided by 10, which should be 7.0 into 10 kgs, which should be 70 kgs. Okay, then a student uses 2,400 kilowatt, so 2,400 watt electric kettle to obtain a value for the specific heat of sunflower oil. Wow, use sunflower oil. It is so costly here, but still people want to use it. Okay, your parents should be really helpful for you in doing this. Shows the apparatus: plug, thermometer, kettle, watch, measuring jar. Okay, the student uses a measuring jar and pours 1.5 kg of sunflower oil into an empty kettle. 1.5 kg of sunflower oil. Okay, 1.5 kg mass is given to you into an empty kettle. Okay, and then he uses a thermometer to measure temperature of the oil. Okay, temperature. Okay, without putting on the socket. Initially, we're measuring this. The kettle is switched on and left for time. For time is given here, 50 seconds. Okay, the temperature of the oil increases by 32 degrees centigrade. I do not know what is the initial temperature. Measure temperature of the oil. So T, okay, is not given. So the temperature of the oil increases by 32. Remember, the final temperature is not 32 degrees centigrade. We do not know what is the initial temperature. The final temperature is T initial plus 32. You see, increases by. If it is increases to, then you can just take the value as 32. Okay, if it is by, then you should use it as initial temperature plus 32. Okay. The student assumes that the electrical energy is transferred as thermal energy to the oil. Whatever electricity you pass, it's being thermal energy. Okay, calculate the value of specific heat of sunflower oil obtained by the student. So we know the heat supplied is equal to mc delta T, right? Now again read the question here. Now let us read. Student uses a 2,400 watts. Whenever there's a problem on watts, the first thing that you should look at is here is that if watts is given, I should be able to convert it to energy. And the next thing that I should look at is time given to you. Because if time is given to you, energy can be written as power multiplied by time. Because power is rate of doing work. Work divided by time. Work is energy. So energy equal to power into time. Okay. Power is work divided by time, which is energy divided by time. So energy should be power multiplied by time. Okay. Let us go down here. Now here you see. So therefore, what is Q? Q is energy. So I will be able to write P into T here. This should be equal to M. M is given to you. C is not known. Delta T, the change in temperature. So here, final temperature, initial temperature 32. So that means TF minus TI is equal to 32. The difference in temperature is equal to 32. So delta T is also given. Okay. So thus, okay, sometimes what you might do is you will just substitute this value here as 32 without doing this one. You won't get a mark here. Okay. If you just substitute 32, you will not get it, but the stepwise you have to show it. Right. Now, mass is 1.5 kg. Let us write down the equation once again. So what is power? 2,400. For how long was this being kept? 50 seconds. It should be equal to 1.5 kg multiplied by C multiplied by 32. Okay. So C should be equal to 2,400 multiplied by 50 divided by 1.5 into 32. Let us calculate what is the value. 2,400 multiplied by 50. Are we doing it correctly? Yes. Divided by 1.5 divided by 32, which is 2,500. 2,500. Let us look at the units. This is watt. Watt is not what? Watt is nothing but, okay, let me write down. This is joules per second multiplied by 50 seconds. divided by 1.5 kg and 32 centigrades. So this goes away. So the answer should be joules per kg per degree Celsius or per degree Kelvin. Both are right. So this should be your answer. Then, if the oil in the kettle is replaced by equal amounts of water, the same energy is supplied, what would be the rise in temperature of the water? Explain. So what we are doing is, I'm going to use the mass of the water to be 1.5 kg. Then this is unchanged. Okay. While the delta T we do not know. Okay, that's what is asked. The oil is replaced. Now, what else can change? If oil is replaced by water, the specific heat of water is not equal to so much. Specific heat of water from the data, as you know, this is 4,200 joules per kg per Kelvin. Now, let us understand what happens then. So, therefore, now once again I can write 2,400 multiplied by 50 is equal to mass is 1.5 kg multiplied by 4,200 multiplied by delta T. I want to find what is the change in the temperature. So towards it, delta T can be written as, now you see, this double zero goes away. 24 into 50 divided by 1.5 into 42. So 24, okay, let me solve it by calculator itself. So 24 multiplied by 50 divided by 1.5 equal to divided by 42. I get the answer as 19.05 unit Celsius. Now, when you switched on the heater for the same amount of time, for the 50 seconds with oil, the temperature difference, the temperature rose by 32 degrees centigrade if it was oil. But if it was water, it rose only by 19 degrees, 20 degrees, which is nearly half of it. What does it tell you? It tells you that water is a great insulator, right? It does not take up the energy so fast. You need to supply a larger amount of energy to increase its temperature. Okay. Suggest an example of a change of state resulting from the removal of thermal energy from the quantity of material. Example of a change of state, removal of thermal energy, which means what? You have to change the state and you are removing the thermal energy. Which one is it? Water to ice. You remove some amount of energy from here, water gets converted to ice, right? Liquid to solid. Okay, you can also give an example like steam to water, right? So that's what happens. Then the effect of the change of temperature on the temperature of the metal. So when water gets converted to ice, this transition happens only at 0 degrees centigrade, which means what? No change in temperature. No change in temperature during a phase transition. Define thermal capacity of a body. What is thermal capacity of a body? We know that Q is equal to mc delta T, or C equal to Q divided by m delta T. Now you can say it is the energy required to raise the temperature of 1 kg of substance by 1 Kelvin. Then a polystyrene cup holds 250 grams of water at 20 degrees centigrade. Water means, okay, the volume and the mass, both are one and the same, but anyway, mass is given to you. Mass is given. Initial temperature is given. In order to cool the water to make a cold drink, small pieces of ice at 0 degrees centigrade are added until the water reaches 0 degrees centigrade and no unmelted ice is present. Specific heat, specific latent heat, everything is given, assuming no thermal energy is lost or gained by the cup. Calculate the thermal energy lost by the water in cooling to 0 degrees centigrade. So what is happening here? You have 250 grams of water, okay, and then at 20 degree, this was at 20 degrees centigrade. 20 degrees centigrade. In order to cool the water to make a cold drink, small pieces of ice at 0 degrees centigrade was added until the water reaches 0 degrees centigrade. Wow. So what is the change in temperature now? Change in temperature is going to be 20 degrees centigrade. And no unmelted ice is present. Specific heat is given, okay. Assuming no energy, thermal energy is lost or gained by the cup, calculate thermal energy lost by the water. Who loses energy? This loses energy. So what we need to do is find out Q is equal to mc delta T. What is M? 250 grams. 250 grams. Let me write grams itself. Okay. And then C. What is C here? Specific heat. Okay. Specific heat is 4.2 joules per gram per degree Celsius. You might have a question saying that why should I put it in grams? Why not I convert it into kgs? I'll give you an answer. Just wait for a moment. Then multiplied by delta T, which is nothing but 20. Okay. Now coming back to your question. See, I could have converted it. But the first thing, I waited for a moment and saw what is this value here. So usually specific heat of water is given as 4,200. What is the unit? Joules per kg per Kelvin. Now here you see it is 4.2 joules per gram per degree Celsius. In case of thermal physics, heat related problems, always see to it that you mention the units along with your calculations, which becomes easy for you. So therefore, now you see if I keep this in grams, here also it's in grams. So I can cancel this grams over here, right? So thus I can just write it just like this over here. So what is this now? 4.2 joules over here. Yeah, joules. So now let us multiply and get the answer for this. This should now be 250 multiplied by 4.2 multiplied by 20, which should be 21,000. 21,000. Now what is the unit here? See, this is Celsius goes away, joules is only remaining, 21,000 joules. So thermal energy lost is going to be 21 kilojoules. Then state the thermal energy gained by the ice in melting. What is the thermal energy gained by the ice? See, ice already has some energy. Okay. So if you give some energy, the ice was like this. It has molecules which are very closely in contact with each other. What did you do? You provided some energy. How did you provide energy? Did you heat it? No, you did not heat it. But instead, you put this ice into a hot water, right? So as a result of it, the energy lost by this water, okay, it was at 20 degrees centigrade. So this heat energy is given to the ice. As a result of it, it takes up this energy and then pushes all the molecules apart, and thereby the ice gets converted to a liquid form. So therefore, thermal energy gained here is also given as 21 kilojoules. And it's very clearly given in the paragraph here. If you need here, if you look at this here, it says that assuming no thermal energy is lost or gained by the cup. So this does not lose or anything over here. So as a result of it, you can consider it here. Now calculate the mass of ice added. Now what's happening here? You observe that the ice is converted to water. Whenever there is a phase transition happening, you should use M into L, right? This is the energy required to break the bond between the molecules so that ice can be converted to water. Now M into L is equal to 21 kilojoules. Now what's the value of L? Let us look at that. The value of L. What is L? Specific latent heat fusion of ice is 330 joules per gram. Okay. So M into 330 joules per gram is equal to 21,000 joules. I am retaining the unit once again. For some reason, we look at it carefully. This joules and joules, I'll cancel it over here. So M should be written as 21,000 divided by 330. This gram goes upwards over here. And now let us calculate what is this value. 2100 divided by 330. 2100 divided by 33. Yeah, which should be 63.63 grams. So I have retained this in terms of grams. So the mass, the amount of mass added is, mass of ice added is equal to 63.7 grams. Then the class is investigating the motion of a steel ball when it is dropped onto a tray full of sand. The figure shows the apparatus. Now what did you do? You have a tray full of sand, you have a steel ball, you drop it. Okay. The moment it drops, I'm not reading the further question. I'm just reading from looking from the diagram itself. Again, a criteria and B and C. Okay. When it falls over here, what can happen? It's the sand. Because of a sand, it can now produce something like this, a rent over here. Okay. A small hole over here. And then it can stop here. Okay. So this is what is my observation. A student is measuring the time it takes for a steel ball to fall through 2 meters onto the stand. He uses a stopwatch. So now when he throws it here, when he drops it here, the distance here is seen to be 2 meters. He uses a stopwatch. He finds out what is the time taken here, t equal to 0. And the moment it comes over, he finds out what is the time taken here. Okay. Then suggest a cause of inaccuracy in the timings. What could be the inaccuracy? The moment you drop it, you will have a reaction time here, right? You will have a reaction time here. You will also have a reaction time here, right? So therefore, reaction time could be one of the inaccuracies. Then when the ball, okay, let me write down reaction time. When the steel ball falls into the sand, it creates a circular hole. That's what is my first observation. Suggest how you would measure the diameter of the hole as reliable as possible. Name the measuring device that you would use. You may draw a diagram. Now let me zoom in. This is how the hole looks like in this way. This is my sand bed. This is my sand bed. It looks like this over here. So which apparatus will I use over here? Can you use a scale? If you use a scale and you press it like this, and you press it like this hole might deepen also, right? So it is always better to use a small stick. I always prefer to take up a stick. I take a stick and gently drop it over here. It just goes and pokes it over here, okay? And then find out what is the height, okay? And thereby I'll find out what is the diameter, what is the radius of it, and thereby 2 times that will give you the diameter of the hole. Okay, so this I can do it. Or maybe suppose if the ball completely goes into it, okay, if the sand once again covers like this, if it covers like this, then this will be the diameter. Then the student suggests the diameter of the hole depends upon the height from which the ball is dropped, because this affects the speed. Definitely, right? Suggest 2 variables on which the size of the hole may depend. What are the factors? The sand should be loose enough. If the sand is loose enough, you can say it's a coarse sand, then definitely the ball that falls onto it might penetrate it much deeper. If not, definitely it will not be able to do it. Okay, this could be one of them. Then secondly, the diameter of the hole depends upon the height, okay, because of x. Suggest 2 more variables. First variable we have suggested. What's the second variable? Can you think of it? What could be the second variable? My connection got snapped off. Okay, now coming back. Yeah. So one variable is loose energy. What is this I have written? Loose sand or coarse sand. The second one is, okay, presence of stone or any other particles present. If it's a fine sand, definitely it can move through it. Okay, it's a wet sand, or maybe if there's a presence of stone or something like this. Definitely, okay. So the particle may not be able to penetrate through it. Okay, then let me move on to the next one. An IB student is investigating the motion of a ball down a slope with an apparatus as shown below. Okay, so you throw a ball here, drop a ball here, it moves across the inclined plane, takes a parabolic path and falls over here. Again, a BNC experiment. Identify the independent, dependent, and control variables in the experiment. What is your independent variable? Now, as you observe here, so this is a slope. Now you see there is something like a plug over here, or maybe a support over here. When you lift this upwards, now what can happen is this ramp can become like this, which means what? The angle of inclination can change. So which means your independent variable will be theta. Dependent. What's your dependent variable? When this falls over here, then the speed at which the ball comes over here, which will be much faster. So as a result of it, it goes much faster over here. And then when the speed is increasing, that means this speed increases, and it's expected that this can go for a longer time, longer distance, and might fall over here, right? It can fall over here, which means the distance here could be a dependent variable. Now, what is your control variable? What are your control variables? The floor is a control variable. The plane, the inclined plane is a control variable. The ball is a control variable. So you can just write the ball, okay, and floor, and then material of the plane. Okay, all these are seen to be control variables. Okay, then she measures the angle theta of the slope, measures, okay, this reduces the ball from the market point on the slope. Okay, she then measures the distance d. This is repeated for a number of angles. See, that's what I have said. Okay, so systematically it has been varied. D in centimeters is given here. Determine the pattern in the value of d as theta is increased. For theta equal to 20, it was 42, 30, 55, 40, 64. Now after this, you see 50, 51, 60, 41. That means initially it is increasing like this for every value of theta. And suddenly, if you still further increase, this starts decreasing like this, right? Okay. So you can say theta increases until 40 degrees. Then it decreases. Whatever is your observation, you need to mention that. From the pattern of results, predict that the values D may be for slopes of 10 degrees and 70 degrees. You need to determine what could be for 10 degrees and what could be for 70 degrees. Now you see, a difference in 10 degree here increases this value by 42 to 55, which is equal to how much? Maybe around 13 centimeter. Another increase of 10 degrees increases this by how much? 64 to 55, 11 centimeter. 11, 13, previous one could be 15 centimeter, right? Which means now what should you do? You should subtract 42 minus 15, which should be equal to how much? Which should be 27 centimeter. So for an angle of 10 degrees, the distance covered could be 27 centimeters. Now in a similar way, let us look at this. For 50, it is 51. For an increase of 10 degrees here, this reduced by an angle of 11 centimeter, distance of 11 centimeter, right? Now in a similar way, for an increase between these two, okay, between these two, we didn't do this one, right? 40 to 50 when I did this. So how much was it? 64 minus 15, which was 13 centimeter here. Now when I go to 70 here, this is 13, 11, then I should subtract 9 here, 9 centimeter, which means this should be 31 centimeter here. So for 70 degrees, the distance fallen could be 31 centimeter. Okay. Then what is it? 10 degree was 27 centimeter and 70 degrees was 31 centimeter. The student is being assessed as much carefully carry out the experiment on her own. She says that it's difficult to release the ball carefully and then be able to see exactly where it lands. Yes, that's agreeable, because the moment you release it over here, okay, you should immediately turn over here. By the time the ball hits this floor, you will not be able to recognize where does it fall here, right? Okay, you will say, okay, well, just it may fall over here. Okay, when you measure it, okay, it may not be the same, so it can either fall here or fall here. It becomes very difficult for us to monitor where does it exactly fall. Okay, agreed. The story is good. Suggests an improvement that she might be able to make up the experiment so that she could obtain a more accurate measurement of D. So how does she get a correct value here? So what is that you can do? What you can do is you can put a sand floor over here. Okay, sprinkle some amount of sand here. Sprinkle some amount of sand, and the moment ball comes and falls over here. Now what can happen is, okay, you can use it. You don't use okay. You can also use a thick bed of sand over here. Okay, when I use a thick bed of sand, so wherever it falls over here, it produces an impression. That impression could be used, okay, further to calculate what is the distance, right? So this could be used. So the modification she can use is strew some amount of sand. Some amount of sand. Okay, along the floor. Along the floor to measure the value of D accurately. Okay, suggests how she might make sure the results of the experiments are reliable. When this keyword is used, say that conduct the experiments, do it multiple times, or trials should be present, should be seen. Okay, see, in this case, what happens is she has done it only for one trial over here. So this should be multiple trial. For theta equal to 20, D1, D2, D3. Then take the average of it. Okay, that's one thing which you need to do. Then, yes, so I think we have come to an end to it. Hope this was helpful. So if you have any more questions, you can just write back to me, or you can watch the video once again to get to know more about it. Thank you, friends.